Hey Chung, I heard you were having some trouble with one of the questions in the textbook, so I thought I'd give you a hand. Here it is. A maximum or minimum is given for the following function. F at x equals 1 over 20 times x to the 3 plus 2x squared minus 15x. Select a strategy to verify whether the point -3, 9 over 5 is a maximum or minimum. Now you can see I've highlighted some things here. The function itself, as that's important as we need to know the properties of the function, but also the point, because that point's going to tell us where we're going to be looking on the graph. Max or min are also very key words because we need to, that's what we're trying to determine, obviously, is our maximum or minimum. But also the word strategy and given, actually, because strategy, it allows us to be a bit creative. In this case, I'm going to be using IROC, but also, like I said, the word given, because we know that -3, 9 over 5 is a max or a min, we just don't know which one it is, and we want to prove that it is a maximum or minimum through which I will be using is IROC. Now, the concepts I'm going to be using, we use in Unit 1 and 2 of our Grade 12 Advanced Functions course. I've written a few steps out on the side if you want to refer to your Unit 1 and Unit 2 notes. That'd be great at helping you figure out this problem. So like I said, we're going to be using IROC, right? So we know that our function is a cubic function, right? So the only type of cubic function we can have, right, because our a value is positive, the only two functions we can have is something that would look like this. This is just a very rough sketch, if you were wondering. And this one, actually, we can't have our cubic function like that because, like I said, given, it's a very key word because we know that -3, 9 over 5 is a max or min. We are just trying to prove it. And in this type of function, we actually don't have any max or mins because we only have a point of inflection, right? So this is actually completely out of the question. Now with this one, you may think, oh, well, we don't have any max or min because as x approaches -infinity, y approaches -infinity. As x approaches infinity, y approaches infinity, which means they both go on forever. But we do have local maxes and local mins, right? And that's what we're going to be trying to figure out, right? And like I said, the key word is local because this function actually does have local maximums and minimums. So we're trying to find IROC at x equal to -3. So first, what we're going to do is we're going to pick two equally distant and close points to x equal to -3. So close is a key word because we want to, the closer we are, the more accurate our tangent line slope is going to be. So I'm going to go 0.0001 away, all right? And that's going to give me -2.9999 and also 3.0001. Right? Now, next step is to find the corresponding y values. And actually, all we have to do is plug -2. Wherever we see an x in our function here, we plug a -2.9999 right there, and we evaluate. And what you're going to actually get is 1.79997. And for -3.001, or sorry, 0001, you're actually going to get the exact same answer, which is very good because this is helping us prove this makes it look like it is going to be a max or min. Now, like I said, I'm using IROC. And why am I using IROC? Because IROC will tell you whether the graph is increasing or decreasing at that particular point, right? So if we have a maximum, right, or a minimum, it doesn't matter, right? If we were to choose that point, right, the graph is increasing at that point. So we're going to get a positive slope, right here. If we were to choose this point, we're actually going to get a negative slope because the graph is decreasing here. But at your max or your min, it's actually the point, right, where an interval of increase changes to an interval of decrease, or for a min, an interval of decrease changing to become an interval of increase. So at those specific points, there actually is no increasing or decreasing occurring, which means your slope is actually going to equal 0 because your tangent line should be flat, if that makes sense. So I'll just show you in a sec how this is actually going to be a flat tangent line, or a tangent line with a slope of 0. So now we're just going to find our slope, as it says right there, m equals y2 minus y1 all over x2 minus x1. So we have 1.7997 minus 1.7997 all over negative 3.0001 minus negative 2.9999. Now it's very important that you keep both those negatives there. You don't want to mess up on your integers. So 1.79997 minus itself is actually going to be 0. Right? And we actually don't even have to calculate the bottom because 0 over anything, I'm just going to say z, right, is indeed 0. So we know our slope is going to be 0. And so we can conclude that this is a maximum or minimum. Now we want to figure out whether it is a maximum or minimum. Now like I said, our a value is positive. Right? So if I were to give a quick sketch of our cubic function we have here, it would look something like that. Right? And if this is a max or a min, right? If we move the smallest fraction to the right in our x value, if it were to be a max, our y value should begin to go down, right? Because if you look at a max, this is your maximum. It means your y value doesn't go any higher in that local area, right? So if we move the smallest fraction to the right of that max, as you can see I've drawn a small point here, you're actually going to get a y value because it's begun to decrease again, right? And same thing for a minimum, right? If you have your minimum, right, and you move the smallest fraction to the right, right, your y value should begin to increase, right? If you notice that. So what I'm going to do here is just look at my points, right? 0.0001 to the right of negative 3 is negative 2.9999, right? So if you notice, at that point, we now have a y value of 1.79997, which actually means that our y value has begun to decrease, right? Because if we compare the point negative 3, 9 over 5, right? That can be rewritten as negative 3, 1.8, right? And 1.8 is indeed greater than 1.79997. So we can conclude that negative 3, 9 over 5 is indeed our max, right? Because if I were to just draw this a bit bigger for you so you can see the big picture, here we go, right? So that's our function, right? If we have our point up here, that's negative 3, 9 over 5, right? And at negative 2.9999, our y value goes down, right? And if negative 3 were to be our min, our y value can't go any lower, right? It can only go up. So in order for us to have our y value go down, negative 3, 9 over 5 must be a maximum, because now we have the point here of negative 2.9999 and 1.79997, right? So that can tell us that it is indeed a max.
See that when I plug our function into Desmos, that I do get negative 3, 1.8, or negative 3, 9 over 5 as our maximum, our local maximum, I should say. And as I begin to zoom in, as we begin to move to the right, our y value begins to decrease, like I said, which would mean our IROC would begin to decrease. So therefore, negative 3, 1.8 is our maximum of our function. Economists will actually use their knowledge of IROC and polynomial functions to predict future markets. As you can see, this is the NYSE Composite Index, and this blue line represents its average over a certain period of time. As you can see, as it grew, its IROC each day would have stayed fairly consistent, not changing too much. Now, what economists will do is when they notice that the IROC for a particular day begins to turn negative, they'll say, okay, so it's been growing at this particular rate for this length of time, and what they'll be able to do is predict the point at which the downtrend or strong downtrend will occur, because these people down here, they've made their money, they want to sell out as they begin to get a little scared that the downtrend might occur after this small decrease in the moving average. So that's one way that the IROC and polynomial functions are used in an everyday world.